Hi, John LeGroux here, founder of Imersiv. In this video, I'll be describing multipath audio technology. This is an entirely new way of thinking about audio. This is a D to A converter chip, a DAC. Today's very best DACs have a noise floor of around 1 microvolt or around minus 120 dBu. These same DACs have a maximum output of around 3 volts or around plus 10 dBu. The difference between noise and maximum level is called dynamic range. Audio circuits have been stuck around this 130 dB dynamic range limit for some time. This got me thinking about a completely different way to approach D to A conversion. And after years of research and development, we've achieved a breakthrough in DAC dynamic range performance. We've done this with a technology called multipath. Multipath architecture obsoletes today's 130 dB dynamic range limit. The new Imersiv D to A converter achieves a dynamic range of over 170 dB. Broadband, unweighted. This is an improvement of 100 times over today's very best DACs. Now, multipath isn't really new. The basic idea has been around for at least 40 years, maybe longer. The problem is, it's really hard to do. Most engineers told us it was impossible. We've spent 10 years perfecting the technology, and the result is a DAC architecture that makes all other DACs technically obsolete. There have been only 3 other dynamic range breakthroughs in the 140-year history of audio technology. And those breakthroughs are the definition of a paradigm shift. We'll cover that history in a separate video. Okay, so what is multipath, and how exactly does a D to A converter achieve 29 bits of dynamic range and linearity? Let's start with a common 32-bit audio file, say a FLAC file, from a USB output. The 32-bit file is then broken into 2 signal paths by the DSP, resulting in a high path and a low path. So we know that conventional D to A converter ICs really can't handle more than about 21 bits of audio data. So we're going to throw away our bottom 3 original bits and transfer the next 20 bits to the low-path DAC IC. And this leaves us with 20 usable bits in the low path and 9 usable bits in the high path. But if you think about it, you'll realize this actually doesn't work. Some of you have probably already noticed that the self-noise of the low-path DAC is far higher than our lowest usable bit, bit 4, and you would be correct. And this brings us back to our DSP. Let's take a look at this somewhat complicated diagram. In multipath audio, this is what we call gain mapping or level mapping. Here's our 32-bit input signal, circled in red. For simplicity, we're going to use a non-standard diagram and refer to bits 1 through 32, with bit 1 being what we call the least significant bit, which is the lowest audio level. Now we're going to feed this 32-bit input signal into our DSP, which is represented by 32 discrete bits. We've designed our system so that bit 32 represents an audio level of plus 28 dBu, which is around 20 volts. Now remember, we're throwing away our bottom 3 bits, so at the low end, we're really only interested in bit 4 and above. So we know that if bit 32 is equivalent to an actual voltage of 28 dBu, this automatically means that bit 4 is equivalent to minus 146 dBu, which is 40 nanovolts. That's 0.0000004 volts, and that's really, really quiet. But this presents a problem. The 2 microvolt self-noise of our DAC IC is vastly higher than our desired bit 4 equivalent noise floor of 40 nanovolts. And this is why we use gain mapping. We program our DSP to shift our low-path input signal upwards by 9 bits. That's a 9-bit shift. So if you look at the diagram, you can see that our original bit 4 is now feeding the DAC IC at its input bit 13. Why bit 13? Well, bits 1 through 12 of the DAC IC are just noise. Bit 13 of the DAC IC is just above the DAC's noise floor. This means we can successfully map our 40 nanovolt signal into our DAC IC. Our entire 20-bit low-pass signal becomes successfully mapped into our low-pass DAC. Okay, so now let's get back to our schematic diagram. The low-pass DAC now represents 20 bits of audio data from -146 to -26 dBu. That's 120 dB, which is 20 bits. But there's another problem. The self-noise of the DAC IC is -112 dBu, or about 2 microvolts. The noise of the IC itself is almost 50 times higher than our desired 40 nanovolts of bit 4 noise. Our solution to this problem is found in the simplest of electronic circuits, the lowly passive attenuator. We feed the DAC output into a -34 dB attenuator, and this does two incredible things. First, it reduces our original input signal back to its proper level, and second, it reduces the noise of the DAC by 34 dB. So now, we have a properly converted 20-bit signal with both a noise floor and a minimum signal level of -146 dBu, or 40 nanovolts. Now let's turn our attention to the remaining 9 bits, the high path. 9 bits is 54 dB. This gives the high path a range of -26 to +28 dBu. When we combine the high path and the low path, we get a range of 29 bits, or 174 dB. That's 29 usable bits, which is 174 dB of true linearity and true dynamic range. But wait, something's still not right. When we sum the high path and the low path, the exquisite 40 nanovolts of low path noise is totally swamped out by the high path noise, which is like 50 times higher. This is a problem. What we need to do is remove the high path when it's not being used. So how do we do that? Well, we add a gate to the high path output. This gate is controlled by the DSP, and of course, it's absolutely sonically transparent and noise-free under all operating conditions. So now, when the high path is not required, its noise is completely removed from the output. And when the high path is enabled, its signal level starts at a very high level. So at that point, the high path noise becomes irrelevant. And that's it. That's how a multipath DAC operates. The end result is over 170 dB of true linearity and true dynamic range. Broadband, unweighted. This is 100 times higher performance than any DAC today. We've covered just enough detail for a beginning understanding of multipath signal processing. If you'd like to do a really deep dive, here are some additional resources to check out. You can start with the AES paper on multipath DAC topology. This is a peer-reviewed paper presented at the 2021 Audio Engineering Society Conference. I highly recommend this paper as it gets into the test and measurement of multipath audio, which is significantly different than legacy single-path audio. Now, if you're a real glutton for punishment, you could read the original patent literature behind the Imersiv DAC, but be warned, it's something like 25,000 words. You could also read the Chinese patents, which, by the way, are really hard to get. You could also explore multipath microphones and ADCs, with patents going back nearly 40 years. Here's a very recent patent. It's my patent for a multipath audio power amplifier. And here's one for a combination ADC and DAC that's designed for 1-bit DSD audio. The future of very high-performance audio is multipath. This includes microphones, preamps, A to D and D to A converters, digital audio workstations, and power amplifiers. Effectively, what we're doing is reducing by up to 2 orders of magnitude the self-noise of every link in the audio capture and delivery chain. Thank you for taking your valuable time to watch these videos. There's a reason we call this technology immersive. You will simply not achieve the same level of spatial and atmospheric realism with single-path D to A conversion. Not even close. Multipath is the next audio paradigm.